Thank you. So let me actually also begin by thanking the organizers for their very kind invitation and for putting together what looks like a very interesting workshop. It's a pity that I can't attend the whole workshop because I have to go back and start to teach. So yeah, I'm going to talk about sum rules, specifically optical sum rules, but from a more low energy point of view. And as the talk progresses, hopefully it'll become clear what I mean by that, and how actually that imposes various constraints on superconductivity, even in regimes where it's not described, let's say, by usual weak coupling BCS type theories. It turns out you can say a lot about even TC and so on without knowing anything about microscopic theories of superconductivity. But before I actually go on with my talk, I just want to take a second and say a few words. As many of you know, it's basically been exactly a year since Professor Amit Datta passed away unexpectedly and prematurely. Now, this photograph is taken from just about 5 days before he passed away last January. And I know that he was supposed to be here and attend this conference and was very excited about it. So I hope this conference can actually be a small tribute to his memory. So before I go on, here are all the people who made this work possible. So Felipe is a grad student at Cornell, Dan Mao is a postdoc, and Johannes is a long-term collaborator, specifically on various numerical approaches that we have been using to tackle this problem. And he's going to move to the Max Planck in Dresden pretty soon. And here's a bunch of references that I'll talk about. I probably won't get to talk about everything, but I'm here today and tomorrow, so catch me anytime if you're interested in knowing more about this stuff. So, because the title had some rules, I'm sure all of you in this room have encountered some rules at some point. Perhaps the first one being this classic TRK sum rule that I think everyone encounters in grad quantum mechanics, which imposes some global constraint on the dipole matrix elements. There are analogous sum rules for the density-density structure factor, the spin structure factor in local moment systems. And they're pretty useful because even when you don't necessarily know anything about the detailed momentum or frequency dependencies of these quantities, they nevertheless provide some general constraints. Now, one feature about all of these sum rules is that they are in some sense UV sum rules, okay? As you can see from the domain of integration, you sum over everything, all the excitations and so on, and you get something. Now, even though they can be useful, one of the things I'm going to be interested in are low energy sum rules, okay? Because for various properties that will be of interest to us, I want to ask, suppose I'm not interested in the entire Hilbert space over, all of the degrees of freedom in the problem, can I still come up with some interesting sum rules, and do they have any relevance to various quantities that might be of interest? And one such property will be superconductivity. So let me jump right in to how knowing something about sum rules can, in principle, put useful constraints on superconductivity. So I'm sure this question has bothered a lot of you at one point or the other. Suppose I start out with a very generic Hamiltonian, which contains many orbitals and bands. I'm going to leave the details unspecified, which is all encoded in the kinetic part of a many-body Hamiltonian. And we are only interested in interactions which have a density-density form. Could be Coulomb, could be something else. Importantly, if you're starting out with density-density interactions, this does not couple to an external vector potential, okay? And so because we are interested in optical conductivities, more generally, we are interested in the electromagnetic response of such Hamiltonians. Now you can ask, what is the maximum possible TC for any such sort of generic Hamiltonian of this type? I'm going to focus mostly on 2 dimensions for reasons that will become clear momentarily. Now, any such Hamiltonian will have some optical conductivity, sigma of omega as a function of omega, that's shown here as the blue curve. Now, when the system becomes a superconductor, let's just, for the sake of argument, imagine a fully gapped superconductor, we know that it develops this 2 delta gap. There is a global sum rule on the total integrated optical conductivity. Now, when there is a gap that opens up, a part of the spectral weight has to go somewhere. Usually, this is what goes into the delta function, the weight of which is known as the superfluid stiffness. And in 2 dimensions, this superfluid stiffness is exactly what determines how high the TC can be via the usual Kosterlitz-Taulis transition. Now, coming back to this question of what is the maximum possible TC, well, we know that the largest amount of spectral weight that could condense into this delta function is the total spectral weight. Okay, so in principle, you can put a bound on how big this quantity can be by the total integrated spectral weight. Now, this is definitely a correct statement, but in any electronic solid that you ever consider, this is going to be an energy scale that is of the order of electrons. Okay, so it serves as a bound, but it's nowhere near being a tight bound, because you conclude, if you apply this argument, that, okay, your TC is going to be smaller than a few electron volts. So the question that we want to consider in the remainder of this talk is, can you put tighter upper bounds where you don't necessarily want to include everything in the problem, but you only include the part of the system that is relevant for the physics of the low energy superconductivity that you're interested in. And this is going to be a short talk, so I'm just going to give you a quick preview of what it is that I'm hoping to tell you about. As will become clear later on, the question is really inspired by a lot of really incredible experimental breakthroughs that have happened in the field over the past few years in the context of these Moiré systems, where this is just a cartoon schematic of what the bands look like. So you have a set of isolated, nearly flat bands, which are shown here in blue, which are well separated in energy from remote bands. From the point of view of low energy physics, you're only interested because the typical interactions are either comparable to or much larger than the non-interacting bandwidth of these flat bands. And both of these energy scales is much, much smaller than the gap to these remote bands. So the low energy physics that I'm interested in is basically these flat bands with the interactions projected to these flat bands. So the question is, if we could come up with some low energy version of an optical sum rule that only makes reference to the degrees of freedom that reside in these flat bands, then that can potentially serve as a much tighter bound on superconductivity. Okay, and again, this is useful because I don't have to make any assumptions about what the mechanism of superconductivity is, where the attraction is coming from, and so on and so forth. And as will become clear as the talk progresses, there are a lot of subtleties that one has to appreciate if one wants to come up with a formulation of this low energy optical sum rule. And once I have sort of this general theory for what the optical sum rule looks like, I'm going to apply it to a concrete problem, again, to a very contemporary problem of great experimental interest. I know most of you don't work on Moiré, so I'm going to be brief here. And hopefully, if time permits, I love thinking about toy models that can be solved exactly. So I'm going to give you an example of a toy model of flat bands with strong interactions. I mean, by definition, interactions are strong because the interactions are going to be the only energy scale in the problem. Now, this is, again, a regime where the standard weak coupling techniques don't work. So I'm going to give you, a set of complementary techniques involving both analytics and exact numerical methods that basically tell us, what controls the stability of superconductivity and various competing orders. And interestingly, even though there is no small parameter in the problem, we're going to introduce a small parameter, which is going to be a quantum metric. For those of you who are not familiar with this object, if you look at the block wave functions associated with these flat bands, you can construct what is known as a quantum geometric tensor. I'm sure everyone is familiar with the imaginary part of this quantum geometric tensor. That's the usual Berry curvature. But the real part also has some interesting geometric information. And when I get here, I'll tell you what that quantity represents physically, and I'll be able to tell you why that is important for superconductivity. Okay. So again, let me just say a few words about the motivation, which is twisted bilayer graphene. So in the past 5 years, we have come to understand a lot about this problem from an experimental point of view, also from theory. So again, this is what a band structure might look like. This is the non-interacting band structure. So in fact, this is not the real physical band structure that the system would actually display, because part of the band structure of these systems is generated by the interactions themselves. But nevertheless, this is the kind of starting point theoretically that people usually begin with, where these are the relevant low energy bands, which when you partially filled, leads to a wealth of interesting experimental phenomena, which are shown here in a representative phase diagram. So in this system, you can accommodate 8 electrons per Moiré unit cell. And what you find is, depending on what the filling is associated with these flat bands, you either get very strong regions of superconductivity, or at every integer filling of these flat bands, you develop some kind of an insulating phase, which is clearly not a band insulator because it occurs at a partial filling of these bands. And one natural question is, what is the interplay between these insulators and the superconductors? Now, more recently, just earlier last year, from direct STM experiments, we have come to understand a lot about the specific nature of these insulators. And one question you can ask is, you get this robust regime of superconductivity. We don't yet know what the mechanism of superconductivity is, but if you think about these insulators that arise as various integer fillings and think of them as a parent state for superconductivity, are there specific properties associated with these insulators that help enhance the tendency towards superconductivity? Okay, and when I introduce the sum rules, it'll become clear, in what sense the low energy physics associated with these parent insulators can have some bearing on superconductivity. Okay, so I'm going to detach myself from details of any particular experimental system for a while now, and just talk about how one should formulate the actual many-body optical sum rule. So this is just for inspiration. Imagine you have any system with lots and lots of bands. This is true for most electronic solids. And again, you want to zoom in to a very special set of target flat bands. Okay? Now, if you, let's say, start out with density-density interactions at the UV scale, the low energy theory that you want to start out with has some form like this. Again, this is the kinetic part of the Hamiltonian expressed in terms of now only the low energy degrees of freedom. So the C tildes that you see here, these are the projected electron operators associated only with the excitations in these flat bands. And you have now also the interactions that have been projected to these flat bands. Okay? So in order to project, of course, you need this projected density operator constructed out of the same projected electron creation and annihilation operators, but which also know something about the block wave functions associated with these flat bands. Okay, that's these U of Ks. Now, if I gave you an effective low energy Hamiltonian of this type and asked you, how do you couple minimally this low energy theory to a probe vector potential, which is of course what you need in order to look at its optical response, how would you do it? Now, the important point to note here is, first of all, the interaction can couple directly to the probe vector potential. It's no longer just a simple, completely local density-density interaction once you include these so-called form factors. But also there is an additional subtlety, which is if you start out with this effective Hamiltonian and couple a vector potential, in principle, coupling the vector potential can take you outside of this low energy Hilbert space. Okay, so if you want a completely self-consistent theory of this problem that is described purely in terms of the low energy degrees of freedom, you want to make sure that you always stay in this low energy manifold. Okay? And there's a simple reason for why that happens. If you go back and think about the microscopic current operator, of course it has matrix elements between your so-called active bands and your remote bands. And you want to make sure that you don't couple to these remote bands and stay in the low energy manifold. With what? No, this is just the non-interacting band structure. Yeah, I'll talk about that briefly. So the point is, just let me address that right away. When you project your interaction to these flat bands, this term itself can generate a many-body bandwidth. And I don't have a slide for that, but I can talk about that later as well. Yeah, but I'm going to mention it. So more concretely, here is what we're after. Again, a priori, we don't know what the effective Hamiltonian looks like in the presence of a weak external vector potential. But even without knowing that, what I'm interested in is this response function, which I'm going to refer to as the diamagnetic response from here on, and the paramagnetic current operator. Now, as I've already alluded to, the important point to note here is both of these in general depend on interactions. So what we want to figure out is what are the renormalized operators that you get when you do this procedure for any electronic solid. Okay? And the key to realize is we need a very systematic prescription that allows us to systematically integrate out all the high energy and remote degrees of freedom. Okay, so there is a well-defined procedure to do that, which I'm going to get to next. But before that, let me just motivate how one can sort of intuitively think about the problem. Okay? So as I said, the quantity of interest will primarily be this quantity. Okay? So the second derivative of the effective Hamiltonian in the presence of a weak vector potential in the limit where you take the vector potential to 0, so within linear response. Now, if you want to calculate this, let's just forget about projection for a while. For your full spectrum, you start out with the Hamiltonian. The first thing you have to do is basically gauge all of your degrees of freedom. So the way to do that is to do this unitary transformation, where you take your Hamiltonian, and basically this is minimal coupling, where you basically take every degree of freedom, you do a gauge transformation. X here is the many-body position operator. Okay, so you do this unitary transformation. Rho is your many-body density matrix. And you're interested in the second derivative, so you calculate this quantity. And you can express this as a double commutator of your Hamiltonian with the many-body position. Okay? Now, you will, at least the experts will immediately notice that if you're starting out with a Galilean invariant system and you calculate this double commutator, this is exactly how you get this standard result that this quantity is simply given by n over m. Okay? Good. So now, this is not what we're interested in. We want to focus on the low energy theory expressed in terms of the projected degrees of freedom. So naively, you would think that, okay, I take my Hamiltonian, I project it. So the P is the projector to your set of active bands. Once you have your projected Hamiltonian, you do the same procedure. You gauge them again, and you calculate the second derivative, and voila, you will have your diamagnetic response. This is wrong. Okay? And it's wrong because when you do it this way, the moment you start with your projected Hamiltonian and do this naive gauge transformation, there's no guarantee that you're going to stay in the low energy manifold that is of interest to you. In fact, you're guaranteed to get outside of this low energy target space. The correct way to do it is to basically do the following. Of course, you take your projected effective Hamiltonian, and you do a gauge transformation, but you now do it with the projected many-body position operator. Okay, so instead of just doing e to the I alpha x, you do e to the I alpha pxp, okay, where pxp is the projected many-body position operator. What was that? Oh, think of alpha as being tied to the charge and vector potential. But ultimately, which interaction? It's minimal coupling, but you have to figure out how to couple to the, your low energy projected degree of freedom. Yeah, ultimately, the linear response, you're taking the limit of alpha going to 0, right? Yeah. What is the pattern? None of this is perturbed. The only weak object is the vector potential. So you take your full many-body Hamiltonian and you couple it to a weak vector potential. So alpha is the strength of that weak vector potential. No, to everything. So this includes coupling to everything. And that will become clear later on. Yes. Yeah. Oh, in principle, it does. But again, all of that will be clear on the next slide when I tell you what's the right way to do it. So basically, there will be a Schrieffer-Wolff way to do it. Wait. Yes, absolutely. No. Very good, yes. Now, you might think that I just pulled this out of a hat, but there is a very nice interpretation for why this is the right answer. Because for your low energy flat band models, there is an emergent conservation law. Even though you're starting out in your full theory with a global U1 conservation law associated with the conserved density, when you're thinking about these projected models, the density only in these low energy flat bands is also conserved. Okay, so if you think about what would be the right gauge transformation associated with this emergent conservation law, this is what would generate that gauge transformation. Okay? Yeah. V over delta. Again, next slide. Yes. Yeah. So good. So all of these questions are exactly answered in this slide. So the right way to do this, and I mean, of course, this is how we did it, is to set up a systematic Schrieffer-Wolff transformation. So again, this is a cartoon of what your problem looks like. So these are the partially filled flat bands that you're interested in. Your interactions are much larger than the bandwidth associated with these flat bands, but smaller than the gap to the remote bands. So this whole procedure is really controlled in V over delta, where delta is the gap to the remote bands. And what you're really doing is systematically integrating out all matrix elements between your target of interest and everything else that you want to integrate out. Okay? So what you want to do now is basically introduce vector potential to this theory and then systematically integrate out, or these high energy degrees of freedom through a Schrieffer-Wolff type transformation. Yeah, I don't want to dwell on this further, but yeah, I'm happy to talk more about this later on. But if you do all this, you will exactly get this nice double commutator structure associated with the projected Hamiltonian and the projected many-body position. Now, of course, some elements of this, not specifically the diamagnetic response, but what the right current matrix element should be, are known from the quantum Hall era, because of course you have a similar question there. What is the role of Landau level mixing? And in fact, the quantum Hall aficionados will appreciate that this PXP is kind of like the guiding center coordinate. So it's kind of natural that that shows up here, even in this context. Okay. Now, the other interesting thing that you can show is that the diamagnetic response, the effective diamagnetic response that I just introduced in terms of these double commutators, is related to a low energy integrated longitudinal optical conductivity, which only integrates up to an energy scale that lies in the gap between the active bands and the remote bands. Okay? So the important point to note here is I may not be able to tell you anything about the precise shape of this optical conductivity up to these cutoff energy scales. So for instance, it could look like this. If you're thinking about an actual many-body insulator, of course, it won't have any spectral weight below the gap, but I will be able to tell you exactly how much spectral weight is contained because it's related to this particular object. Now, everything I've told you looks deceptively simple. It's not, for the following reason. So if I were to now focus, I think this addresses your question, on what is the precise form of this double commutator, it basically is controlled by two objects. The first is that you're dealing with a many-body theory. It actually includes a correlator associated with 4 fermions. Okay? This is the interaction contribution. The bare contribution coming just from the kinetic piece is trivial, and I'm not writing that here. Okay, so there's that. And then in addition, because of the way the form factors come in through the projected interactions, there is another piece which has a very elegant form, which is basically given by a covariant derivative associated with these form factors, where these curly A's that you see, they are basically the non-abelian Berry connection associated with your form factors. Okay, so of course, you should have anticipated this, but the way this is written, this is manifestly gauge invariant. Now, if you stare at this and you focus on concrete examples of, let's say, flat bands with some non-trivial block wave functions. And if you were to take a Fourier transform of this into real space, you can convince yourself that this generates all kinds of non-trivial contributions, which includes an interaction renormalized bandwidth, a pair hopping interaction, and so on, which of course, all of these couple to a vector potential. And all of that is included in this very general looking form that I have. Now, one of the beauties of this whole approach is that, usually when we think about minimal coupling, you do some Piles type substitution. And so you might think I need a real space description of my low energy model. But the beauty here is that I don't ever have to make any reference to a real space picture for these flat bands. And I can set this up entirely in momentum space, which is useful, especially when we are dealing with topological bands, which may not have exponentially localized Wannier functions and so on. Okay, so now, nevertheless, if you want to actually go ahead and calculate any of this, this is difficult to evaluate exactly unless you've already solved the problem, because generically speaking, we don't know how to calculate these 4 fermion expectation values. Now, one approach is to just try to bound these correlators and put some conservative upper bounds, let's say, on what is the largest optical spectral you could ever get. Or if you already have a problem that can be solved in some limit, you can try to evaluate this, okay? And let me quickly mention, so turns out in twisted bilayer graphene, even though this is obviously sort of a strong coupling problem, there is a limit where you can calculate these correlators exactly. And this goes back to this so-called chiral flat band limit, which you get when you ignore the single particle dispersion completely and a very specific hopping between the 2 layers, because in this limit, the problem actually decouples into something that looks like multiple copies of Landau level-like wave functions, but in a time reversal symmetric fashion. Okay? And in fact, in that limit, the physics of these various insulators that show up at integer fillings is quite remarkably similar to some quantum Hall ferromagnet type problem. So why is it that in this limit you can solve the problem exactly? Well, because turns out at all the integer fillings, these quantum Hall ferromagnets, they're kind of like Slater determinant states. Okay, so these 4 fermion expectation values that we had to calculate in order to evaluate the spectral weight, you can use Wick's theorem. And so the general picture is this: you have an insulator in the low energy manifold. So there's an interaction-induced many-body gap. I'm calling that delta insulator. So of course, you know that there won't be any spectral weight below this gap, but you have a bunch of filled states and a bunch of empty states. So in principle, the sum rule should be able to tell you what is the, what are all the optical transitions and how much spectral weight can you get in this low energy manifold because of coupling to an external electromagnetic potential. Now, if we can figure out what this quantity is, this will serve as really a rigorous low energy bound on any superconductivity that stems out of doping away from these insulating states. Okay, now if you do the brute force thing that I just told you in momentum space, it has a bunch of stuff. The details are not important. The important point is when my students started evaluating this brute force, he would keep getting a 0. Okay, that's weird. If you have a low energy manifold, you're calculating the total low energy spectral weight in some many body state, and you keep getting a 0, I mean, either it's a bug or there is some interesting physical reason why these insulators don't have any low energy spectral weight. And it's clearly the latter. So the way to see that is if you start out with this double commutator that I wrote out for this diamagnetic response, you can shuffle around the terms and you can re-express that as a double commutator of the many-body position with the actual density matrix, the many-body density matrix. Now this is where the dependence of this spectral weight on the actual many-body system comes into the picture. It turns out that in this so-called chiral flat band limit, where the problem basically becomes multiple copies of Landau levels, the actual ground states that you get have a very interesting property, which is that they don't have any dipole matrix elements between the filled and the empty states. So if you start exactly from the solvable limit, this low energy optical spectral weight just vanishes identically. Okay? If you're interested, I can go more into this later on. Okay, now, of course, to be clear, real twisted bilayer graphene obviously is not in this limit. There are all kinds of what we think are small perturbations that take you away from this limit, but this serves as an interesting starting point to put real bounds on superconductivity. So of course, at this point, you want, as you go away from this point, you don't have full analytical control, but you can nevertheless do this. And if you take the right starting point, which we believe is relevant for twisted bilayer graphene, you can now put bounds on superconductivity, which are much more conservative compared to what we had earlier, 6 MeV or 60 Kelvin. Okay, I have 5 minutes, so let me now move to the other thing that I wanted to talk about briefly. Okay, so twisted bilayer graphene is very complicated. So let's take much simpler toy models of flat bands with interactions. Specifically, I'm going to take a model of mathematically flat bands, whose dispersion I'm going to show you in a second, with strong on-site attractive interactions and nearest neighbor repulsion. Okay? The actual bands have a dispersion that looks like this. Of course, everyone can diagonalize this in their head, I think. If you diagonalize this, of course, you get two flat bands with energies plus and minus t, simply because sine squared plus cosine squared is 1. Now notice that the taus, their Pauli matrices is acting on some orbital degree of freedom. There are no tau z terms here. So in fact, the Berry curvature associated with these flat bands vanishes identically everywhere in momentum space. Now, this alpha that you see here, this has some weird form, where the only thing that you need to pay attention to is this quantity zeta. So when zeta is 0, this represents a problem where there's basically no hopping between different sites. And zeta can be tuned as a small parameter because zeta is exactly what represents this quantum metric that I had introduced earlier. Physically, what zeta really represents, so these are flat bands, but they're topologically trivial. So you can construct exponentially localized Wannier functions. And zeta is basically the minimal spatial extent associated with these Wannier functions. So even though we will be interested in a problem with interactions projected to flat bands where there are no small parameters, you can use zeta as a small parameter to first gain some analytical insight into what the interacting theory looks like. Okay, so this is like a cartoon picture for what the projected theory would look like. You construct the Wannier functions. The size of these blobs is controlled by the small parameter zeta. And if you write down the low energy theory in the Anderson pseudospin notation, you generate a whole bunch of terms, okay, which are controlled in a small zeta. So these terms are actually precisely your pair hopping interactions, okay, that are generated when you project your attractive on-site interaction to these flat bands. This is a nearest neighbor density-density interaction. But you can actually also show that the same small parameter zeta generates a term like this, which is like an interaction-induced dispersion. Okay? So without having to make any weak coupling approximations, you actually know exactly what the many-body Hamiltonian looks like. But the beauty of this model, which I didn't tell you before, is that in addition to this small zeta expansion, this model doesn't suffer from a sign problem. So in fact, you can do non-perturbative quantum Monte Carlo and obtain the full ground state phase diagram, okay, at any value of zeta. This is what the phase diagram looks like. So your dominant interactions are on-site attractions. So you would have thought that's going to lead to pairing, because zeta, which controls the degree of delocalization associated with these flat bands, that can generate pair hopping, and your system is guaranteed to always be a superconductor. That's not the case. Even if you turn up an infinitesimal nearest neighbor repulsion at an integer filling because of commensuration effects, you actually get an insulating charge density wave. Okay? So you have an insulator. Now, of course, if you deviate away from it at a generic incommensurate filling, the system can't stay an insulator. But interestingly, without melting the long-range CDW, it also gives rise to, so the excess dope carriers, they become a superconductor. So in fact, what you get is a supersolid. Okay? Yes, one, yeah. Now, you might think that if I'm at a commensurate filling, and if I have a nearest neighbor repulsion, I'm going to stay an insulator forever. It turns out this is where, again, the non-trivial aspects of these, the block wave functions, which encode the property of the quantum metric, come in. You can stay here and simply drive up. Let me skip this. Simply drive up this parameter zeta, which is, again, the spatial extent associated with these Wannier functions, and drive the system from a CDW to a supersolid without going away and doping. So simply from just driving up by how much these wave functions are localized or delocalized, you can drive the system from a CDW to a supersolid. Okay? And this transition turns out to just be a 2+1 dxy transition. Okay, so here is an outlook. The key point I want you to take away is, if you want to think about electromagnetic response associated with these low energy Hamiltonians, you have to be careful. If you want a consistent description, the right way to think about it is in terms of these projected many-body position. Now, of course, this can be extended to other response functions, to nonlinear sum rules, something that we're thinking about. And you can now, instead of just thinking about projected models, you can think about, if I start from some high energy, can I extend the Schrieffer-Wolff to come up with some, scale-dependent electromagnetic response in some, RG type framework. And this bit was probably a bit rushed, but in the key message is, when you're thinking about flat bands and interactions, it's a non-perturbative problem. So interactions projected to these flat bands can trigger a host of competing instabilities. So we need a lot of new methods to tackle that problem. So I'll end there. And yeah, these are again the people responsible for all the work.
Let's thank the speaker. So questions? Yeah, Rajdeep.
Whereas the insulating gaps that you get are probably due to splitting of the low energy band itself, right? Because they are very small.
Yeah.
And so how is a theory which is controlled by going to higher bands going to give you a reasonable bound?
Oh, okay, good. So maybe this was not clear. Let me just go back to the picture. Again, the Schrieffer-Wolff is a controlled expansion in V over delta. When I tell you this result, this is basically in the limit where delta is now infinity. You don't have those, because this is expressed purely in terms of only the low energy degrees of freedom. So this makes no reference whatsoever to the remote bands. So now everything here is the theory purely for the flat bands with the interactions projected to these flat bands. So the gap to the remote bands at this point has no bearing. Also, for all these calculations in the context of TBG that I presented, delta is basically infinity. Now you can ask what would be the leading correction because of the presence of the remote bands. And that's going to be an additional correction to everything that I showed, which you can go ahead and calculate, as, basically it'll be like V squared over delta and so
on. Okay, any other questions? Well, if not, let's thank this. Yeah, sure, go ahead.
Great. So if you take just a normal Landau level in the projected theory, this quantity is going to be 0 because of the emergent dipole conservation. So if you take just a spinless Landau level with density-density interactions projected to the spinless Landau level, at any filling, it can never be a superconductor. And that's because the sum rule is saturated at the cyclotron frequency, which is not a part of the low energy Hilbert space.
For the spinful one, you can...
Yeah, of course, sure. Yeah. So again, yeah, we can talk about this, but ultimately it's again tied to the emergent dipole conservation.
Okay, if there are no further questions, let's thank the speaker once more.